Hello everyone, it's me Theo again. Today we just want to continue the discussion on boundary layer flows. So in the last video, we found that our velocity profile was looking a little bit strange. So for boundary layer flow, we should expect that the velocity outside the boundary layer is pretty much uniform. Except in this case it is not. So we want to find out what's wrong with our simulations, whether we did our boundary conditions correctly, or was it a case that the mesh was not fine enough. Now what do I mean by the mesh is not fine enough? You can see that in OpenFOAM simulation they basically solve the partial differential equations by discretizing the whole problem into little boxes. So you can see in this wireframe diagram that's being shown here, one of the problems that can arise in simulations are that these boxes are not small enough. So if these boxes are not small enough, that could result in some kind of error in the calculation, and to test if that is the problem, we want to see if we can make these boxes smaller. So that is called increasing the mesh resolution. It's making the resolution higher. And you'll see what the effect is, and we'll try and find out if that is really the problem that we have. So anyway, we're going to continue with increasing the mesh resolution, making the mesh slightly more fine. So I'm going to navigate to my OpenFOAM file directory. I'm going to copy a flat plate case into a flat plate fine case. Okay, so I'm just going to copy that over. So let's navigate there. Okay, so let's clean it up. Okay, and let's change the run file. Okay, so that when we finish our flat plate simulation, we will have a flat plate fine.foam output file. So that will be it. Okay, now what can we do, let's say, to increase the mesh size or increase the mesh? So I'm going to increase the mesh resolution. So I'm going to go to the system file, and the mesh resolution is controlled mostly by the block mesh dict file. Okay, so where can we find this mesh resolution? If you scroll from the top, you will see this thing called scale, vertices, and then you'll see this blocks entry. When you see this blocks entry, you'll see some the definition of many blocks in OpenFOAM. In this case, it's just one. It says hex 0, 1, 2, 3, 4, 5, 6, 7, and it says 20, 20, and 1. And then it says simple grading 1, 1, 1. Now what does this 2021 means? It means 20 boxes in the X direction, 20 boxes in the Y direction, 1 box in the Z direction. And in the Z direction we don't really care, so it doesn't really matter anyway. Okay, so first thing first, I'm gonna try increasing from 20 by 20 to 40 by 40. Now this should increase our mesh resolution. So I'm going to save this, escape:\wq, and I'm going to execute the run command. And we see that we have some kind of error that is happening. And what is the error here? Let's Let's go and find out by looking at the output. Okay, I'm gonna start from bottom. It says foam fatal error, continuity error cannot be removed by adjusting the outflow. Please check velocity boundary conditions and or run potential foam to initialize the outflow. What does it mean? Well, if you can imagine all these boxes here, on the left side it is on the left side it is a fixed boundary condition where the velocity is fixed, the x velocity is fixed. Here at the bottom it's a no slip condition. Now, if the boxes are so small, and then OpenFOAM is going to look at each of these boxes and solve them one by one, sometimes you'll run into, let's open Paint. So let's say you have one box here. At the bottom, you have a no slip. And at the side, you will have a fixed velocity. Now what happens is that we have many boxes. Okay, let's draw a second one, and then right, third one on top, and then another one here. Okay, now if you make these boxes smaller, like say the 40 by 40, it will be something like that. It's a very crude drawing, but should do the case of illustrating. Now, if let's say you have this box here, now OpenFOAM is going to say, okay, here I will have a some velocity that's coming in, and then here there's a no slip condition, which means it has to be exiting either here or here. Okay, and then OpenFOAM says, hey, okay, here I'm gonna have another one in, and it's gonna exit by here, here, or here. If you increase the mesh resolution, sometimes when you start the problem, initially your velocity here is going to be 0. This is your starting velocity based on the U input files. So let's take the U input file first. CD0 and VIU. You see that the internal field here is a uniform 0, 0, 0, which means at the start of this simulation, OpenFOAM will assume all the velocity in every single box is 0. Okay? Now, so what OpenFOAM does is it's going to try and adjust the 0 values, okay, of this box here, and maybe this box. And then it's going to move up one square, and it's going to try to change the values of the velocity in this box and in the adjacent boxes. But what happens if you make the mesh so fine that you encounter lots of these small little zeros? OpenFOAM's going to be a little bit confused. That's okay. If the velocity here is 0, and then the velocity here is 0, one of these must change, because if there's flow coming in here, flow's got to be going out here somewhere. But if this is a no slip, then maybe the velocity here you can't quite change this velocity, because the condition over here is a no slip condition, which means at the bottom is like a stationary kind of thing. So OpenFOAM is stuck and says, okay, maybe this speed cannot be that high, so I need to increase my velocity here and here. But when OpenFOAM looks at this one and then it says, oh, okay, I'm looking at more zeros, then is the flow supposed to go here, supposed to go here, or supposed to go here? Now if the mesh isn't so fine, OpenFOAM can fudge it by changing some of these zero values and increasing the velocity to make the flow go elsewhere, so that the solution can converge and be solved. But if you have such small boxes, OpenFOAM has to do this again and again, and you'll get really confused. You have to do it like almost twice to 4 times as much if you just increase the mesh resolution. So to prevent this confusion from happening, and to prevent OpenFOAM from trying to guess what all these values are instead of zeros, you need some kind of initial guess. Let's give OpenFOAM a little bit of a helping hand in that sense. Maybe here the velocity, we will expect it to be 1. Here the velocity is a bit faster, we expect it to be 3. So we could actually manually input all of these, but that would be very troublesome. So instead of that, what we want to do is to do some initial guessing first. So what we're going to do, we're going to use the, we're going to use the coarse mesh flow profile. That means our initial guess is going to look something like this, and then we will use this to try and calculate what the fine mesh flow profile looks like. Okay, so if you would actually look at OpenFOAM, the tutorial guide, it actually shows you how to make how to do this. So in fact, it says over here you want to map the coarse mesh results onto the fine mesh. So this is something we're going to try and learn in this tutorial video. Okay, so first thing first, let's make it easy. We will go to System. Okay, we're going to clean it up first. Let's go to System, and we're going to look at block mesh dict. And then we're going to revert this back to 20 by 20. Why are we doing 20 by 20? Because we want the coarse mesh results, which is the initial flow field that we are having. And we are going to simply do a let's go to see what we're supposed to do. We'll do a block mesh icofoam to run the thing again. Let's go. Block mesh icofoam, and that will give us the initial values. Okay, so 0.1, 0.2, 0.3, 0.4, 0.5. And then we'll want to use this 0.5 seconds as our initial conditions. So let's go to the run file, and let's remove this all clean, because that will remove our 0.5 time step. Okay, so we want this 0.5 file to start. So what are we supposed to do? Well, first thing, let's go to System, and then let's go to this file called control dict. Okay, and it says it starts from the start time, and the start time here is 0. So instead of 0, we want it to start from 0.5. So let's give it the start time of 0.5. Now that's just one part of the problem. There are many more steps to go. Next thing, of course, we want to change our block mesh dict. We want to change it to 40/40, because now we want to have it calculate the fine mesh. Okay, so that is the next step. And then the other thing is we'll want to use this mapFields. And what is it going to do? This mapFields utility is going to look at your start time, which is a 0.5. It's going to look at your start time, and then it's going to convert this from a 20 by 20 mesh into a 40 by 40 mesh. So let's see. It says mapFields ... / cavity consistent, but cavity is their the file that they want to change. Okay. So instead of let's say alright, we're gonna try that. Yeah, instead of putting this cavity down, we're gonna use flat plate instead. So let's go mapFields ... / flat plate, and then it says consistent. Okay, and here we have our results, and let's take a look at the 0.5 file. VIU, and let's see, there's a 400, and then we'll have all these values over here. Now it should be 400 and not 200. Let's see, CD 0.4, CD 0.4, and let's see the VI of U. You see, okay, 400, yes, 400 is correct, yes. Sorry, what I meant is you probably expect something to be a 1600, because 1600 is the kind of what do you call that? 1600 is 40 by 40. So you want the mesh starting at 40 by 40, not 400. So it says here, source mesh size 400, target mesh size 400. So that's not refining the mesh at all. So what we should be doing is that we got to change this target mesh size to 1600. Now let's see how we're supposed to do that. Okay. Right, let's take a look at what it says about the mesh field. Okay, let's take a look. Mesh field. Right, I think I made a mistake. Okay, let's cancel this. Alright, I think I know what's wrong. I made a mistake here. Okay, let's do a cleanup first. And then we're not supposed to, run the block mesh from here. Okay. So what mapFields does, we're going to explore that very shortly. So let's go to System, VI block mesh dict. It's a 40 by 40. Now previously when we ran block mesh, it's actually a 20 by 20 file. Okay, so what were we doing just now? We did the block mesh icofoam to generate this 0 to 0.5. Now when we did this, the block mesh file that was generated had a 20 by 20 mesh resolution. Now if you want the 1600 mesh resolution, we need to run block mesh again, so that we can generate a 16 by 16 resolution. So let's just carry that out. So we have a 40 by 40 already, you can see here. So let's run block mesh. Alright, so now block mesh is done. We can start using the mapFields utility. So mapFields, so I'm going to go to the run. Okay, so the block mesh is there. Let's do the run. mapFields flat plate, because we have a flat plate file just kind of in the same folder, and then we're going to write consistent. So I'm just going to exit it like that, but for demonstration's sake I'm going to run it manually first before doing it in the script. So let's do mapFields flat plate consistent. Let's go. And now look at what we have. We have a source mesh size of 400, target mesh size 1600. Perfect. That's exactly what we want. So just to recap, we are still using the 0.5 output file, and what mapFields does is that it goes to look at this. It goes to the flat plate. What mapFields does is it looks for this file, this 0.5 file. It copies it over to our flat plate find folder. Oopsie. CD flat plate find. It goes over to our flat plate find folder, and it copies it here. And not only does it copy it there, it increases the mesh resolution. And you see 1600. It will convert the 20 by 20 into a 40 by 40. And how does it know to convert it into a 40 by 40? It will have to check the block mesh dict file in the local directory which you have just run. Okay, so that's why we need to run block mesh dict, because block mesh dict tells the mapFields utility to move into a 40 by 40 mesh size. So we are almost ready to run. We have a suitable initial condition. We have a correct block mesh dict, and we go to the control dict. We start from 0.5. Now one more thing we need to note. Now look at this part. It says control adjustments. Control adjustments. It says that delta t should be set to 0.0025 seconds in the control dictionary directory. So it says here delta t, that's the time step, is 0.005. And because we have increased our mesh size, mesh resolution, we need to make the time steps shorter. Why is that the case? Now let's go back to our paint. Alright, And we'll have, let's say, this box here to indicate the mesh. Here and here. Okay, so let's say we have a box here, let's give it a random number, 0.5 cm long. Now, and let's say time step equals to 0.1 seconds, for example. But the flow velocity equals to 1 meter per second, or 100 cm per second. What's going to happen here? If you look at each time step, every time step we move our fluid by 0.1 times 100 cm per second. That's 10 cm. So basically, in one time step, the fluid has moved from this box, and then it moved like 10-20 boxes down the row. And that's going to be a problem. It's going to make our calculations very weird. So in any like say time within the time step, preferably speaking, you should not move more than the fluid should not move more than the space of one box. And that's kind of the general idea behind making the solutions stable. If not, they're going to give you very funny results, and then you're going to have error. So we need to reduce our time step. So the actual terminology is called making sure the courant numbers, C-O-U-R-A-N-T, the courant number, I just typed it there, is small enough. But I'm just explaining it in a more casual kind of way, so that it's not so abstract. I try not to abstract it too much. So if we want to make sure that this 100 cm per second flow doesn't move more than this 0.5 cm, what should our time step be? So our time step should be 0.5 divided by 100, and that will give you 0.005 seconds. So your time step should be 0.005 seconds or less. Now, what happens when we increase the mesh resolution? So let's say our new boxes are half the size. Okay. Now if our boxes are half the size, you see again that we have the same problem. If you use a time step of 0.005, the fluid is going to traverse more than the length of one box. So in order to mitigate this, we kind of have to half the box, half the time step. From 0.005 to 0.0025. Now that's the basic idea, that when we increase our mesh resolution, we have to decrease our time step, so that the fluid, so-called, doesn't flow across one box, doesn't flow across the more than the length of one box within one time step, and thus screw up our calculations. So it should be 0.0025 in this example or less. Now, previously, when we have 0.005, our output was stable. So instead of 0.005, we want to change it to 0.0025, because we changed from a 20 by 20 mesh size to a 40 by 40 mesh size. So we have half the size, half the length of the square, and thus we need to half the time step. That is the rationale. So let's WQ And now we want to run icofoam. As per normal, we're going to ignore the rest of the steps here, because this is an interesting thing you can do, but it's not necessary. So let's just run icofoam. What does it say? Create time, create mesh time. Okay, what does it say here? Create time. Create mesh time for time equals 0.5. Piezo mode. Reading transport properties, reading field P, reading field U. That means it's looking at the initial conditions. And then it says reading, calculating phase, flux, field, and phi. It says starting time loop, and then it says end. What does it mean here? Well, let's take a look at our system and let's look at our control dict. And then it looks, what is it here? We have a start time 0.5, end time also 0.5, which means that it's not going to run anything. So that's a bit of a mistake there. My bad. But that's pretty easy to rectify. Let's change our end time to 0.7, and then it should solve the problem. So let's run icofoam again, and now it should run as per what we expect. So we're going to touch flat plate fine.foam, and now we're going to try and run it in visualize it inside our we're going to try and visualize it inside the paraview. So let's go here and we'll look at our OpenFOAM file. Wrong one. OpenFOAM file. Open flat plate fine. So let's copy this over here. Flat plate fine, and then we will open flat plate fine. So let's look for flat plate fine. We'll just copy and paste there, and then we'll apply. So looking at this is the same pressure spike at the bottom left hand corner, and let's take a look at the U velocity profile. It's still the same. Okay, we gotta be make sure. You see the time here is 0.2. We need to change it to 0.5 and above, and then we can see the mesh resolution is increased. Let's look at the wireframe. See, we have increased the mesh resolution successfully, but the velocity profile still looks kind of funny. So from this we can conclude that the problem of this kind of velocity profile is not caused really by the mesh size mainly, but it could be something else. But in this video we have already covered the basics of creating a finer mesh and how to do it in OpenFOAM, and we have started, we have found that okay, the mesh size isn't the problem in this case. So let's take a look at other potential issues, and let's see whether we can find the root cause of this problem elsewhere. Thanks for watching, guys. I'll see you guys next time. Bye bye.